Thank you very much to everybody for being here and for your interest in our science. And thank you, Edouard, for the invitation. So I will try to give you a few insights and lead you through a story about how to represent the meridional overturning circulation in models and what can we say about its drivers. In the end, why is this circulation here and how is it driven? As a disclaimer from the beginning from my colleague oceanographers, this is just a story through the drivers of the MOC. Within 40 minutes or so, I cannot be exhaustive, and the idea is just to give you a flavor of the various mechanisms that we are investigating, and also perhaps about our uncertainties at the moment, what we still don't understand. A second disclaimer is that I will mostly focus on the Atlantic meridional overturning circulation. Edouard has nicely introduced how global this circulation is, but here I will focus on the Atlantic part, and I will not be able to prevent myself from using this pretty ugly acronym, AMOC. So now you know this relates really to this large-scale oceanic circulation in the Atlantic. So why should we be interested in the AMOC? We've had a long introduction, so I will go fast on that just to show you perhaps this figure here that tries to summarize from the literature the various impacts that have been documented in case of a collapse or a weakening of the MOC. So many authors are interested and are trying to understand what happens if the MOC is reduced. And you can see that you have all sorts of consequences, both on the physical system, biological system, and human-managed systems. And all over the globe, and mostly also still concentrated in the Atlantic. So the MOC is a major player of the heat redistribution between the equator and the pole and within the Atlantic Ocean. So this is in case of a collapse. Why would we have a collapse? Why are we interested in the collapse, or why do we think that perhaps the MOC could be reduced? And this is mostly because of these kind of simulations. So this is a summary of the response of all the climate models that Pascal showed just before. This is time here, and this is the strength of this oceanic circulation as modeled by all the models that are available around the world. You can see that for the moment, the models consider that the circulation is relatively stable, but it is expected to decrease within the 21st century because of the effect of various external forcing, and in principle, this little molecule here that stands for CO2. But even without the CO2 and even the greenhouse gas effect, we will see that the MOC varies. It varies because of internal variability of the climate system. The climate system is composed mainly of the ocean and the atmosphere. These are two fluids. Fluids are largely chaotic, and especially when they begin to interact together. So the climate system is cannot be represented just by a line, but has internal variations around an equilibrium state. And this figure here shows the impact, so the temperature at the surface of the globe associated to natural and internal variations of this circulation. Such a figure can only be obtained in a model because, as Pascal nicely explained, we don't have yet a nice picture in the observations or long enough description of the variations of this oceanic circulation in the models, in the observations. But in the models, you can see that natural and internal variations of this circulation induce anomalous temperatures, anomalous warming. For example, if the circulation increases, an anomalous warming of about 0.3, 0.4 degrees on average over the northern hemisphere, just because of modulation of the climate system. So now, as an oceanographer, I'm also interested by the AMOC for another reason, because I consider that it is a helpful conceptual description of the oceanic circulation. The real oceanic circulation is not this one. Edouard has showed us this schematic, and he has introduced all the disclaimers saying that this is a strong simplification. We don't have a full description of the oceanic circulation yet, but here, if you look in a very high-resolution climate model, you can have a first flavor of what the oceanic circulation rather looks like, and it is more something like this. You can see with lots of eddies and turbulence at all kinds of scales. This is a picture of oceanic currents in an oceanic simulation at 1/12 of a degree. And you can see that this is just in the surface. And so, of course, that's very interesting. And Anne-Marie will tell us right after a lot about the effect of these eddies. This is too simplified. This is something in the middle. This is just a sketch from what we tend to understand about the circulation. And the EMOC lies perhaps somewhere in between all this. Mathematically, as a modeler, I consider that the EMOC is the integral. So this is more or less the sum that Pascal was showing us earlier. The integral over depth and over latitude between the east and the west of the oceanic basin, in particular of the Atlantic, of the meridional velocity. So you integrate all of the velocities that flows northward through a certain section. And as a modeler, I am happy enough to know the velocity field everywhere and to be able to proceed to long-term averages. I can average everything and I know the velocity everywhere. So as opposed to Pascal, I am able to have a 2D view like this of the oceanic circulation. It's only 2D here because remember that I have been integrating over latitude from the western to the eastern corner, eastern end of the Atlantic. So you have a view like this as a function of the depth, as a function of z, and as a function of the latitudes from 30 degrees south, which is the southern edge of the Africa, until the north. And this is a stream function, so here the positive values show you a circulation in this direction as represented by the black arrow, and negative values in the other way around. And all this is expressed in Sverdrup, which are millions of cubic kilometers, millions of cubic meters per second. Okay? All right, and so we have a maximum amplitude of this circulation of about 12 Sverdrup. Another view that I will be using in my talk here is when I consider, for example, a section here at 30 degrees north or 26 degrees north, and the advantage is that I can compare now profiles of this circulation. Here is for different configurations of one climate model, and here this is compared to observations that are taken at 26 degrees north. This is the rapid array that Pascal has been presenting just before. And finally, a final representation that we use in climate models is this one. So it is very similar to the one I've shown before, but now it is expressed in terms of density of the water. Because ultimately, the EMOC, this large-scale circulation, is something like a change of density of water masses as they flow towards the north, in the North Atlantic. They get cooler and saltier, and then they eventually are strongly mixed with depths and change their density before returning to the south. So this is also a very important representation that helps us to remember that it's not just about one little duck in plastic that flows towards the north and then kind of sinks and flows back towards the south always at the same level. It's also a matter of water mass transformations. Water masses are mixed together and they can change their properties as they flow in the ocean. All right, but let's go back. I mean, we've been criticizing enough this schematic, but as you can see, we keep going back to it because it is still helpful. It helps us to simplify our view. So now let's go back to what we understand or what we believe sets this circulation now in the mean state. Simply, why do we have at all, where do we find the energy to have this circulation? So this schematic here is taken from a website of outreach that is very interesting. I encourage you to regularly look at it. And we have different possible drivers. The surface cooling and water mass transformation in the North Atlantic, we've been talking about it quite a lot. There is also, as a usual suspect, the mixing at the interior of the ocean that can help the deep water masses to mix and come back to the surface and thereby feed the surface flow that flows to the north. So mixing in the interior or at the bottom of the ocean is also a suspect. And then finally, there is also a largely suspected drivers in this Austral Ocean here that is very specific in the geography of the world ocean because as you can see, This is the only place in the world ocean where the currents are able to go around the Earth without finding any continents on their route. And we also have very intense winds in this area, as you probably know. And these winds drive what we call an upwelling. So because of a divergence of the wind, the waters are sucked towards the surface. And this also feeds, as you can see, some water that then is trying to flow within each basin, and in particular in the Atlantic. We also have a very strong turbulent activity in this region. These are the eddies that are counteracting the effect of the upwelling, and this interplay between the wind and the eddies is also a major driver of the circulation in this region. So how do we progress now? This comes from very old oceanographic ideas, and how do we progress? One of the first steps to progress, oceanographers, and in particular this has begun more or less with Stommel in 1961, have tried to conceptually model all of these processes using so-called box models like this. So here I tried to put it in the shape of the Atlantic. But now let's not hurt our head too much and put it back in the right direction. So this is what people do when they try to understand like this conceptually the oceanic circulation. They try to account, for example, here in the North Atlantic, for a flow that would go from the upper ocean to the Northern Ocean and sink like this in this region. So this is the northward transport, which is believed to be proportional to the difference of density between the northern North Atlantic and more of the tropical North Atlantic, one would say, so the center of the Atlantic. And this is considered to be a sort of a preconditioning for the oceanic circulation. It has to be there. It's not necessarily from there that the energy comes, ultimately, but it has to happen to ensure continuity of the circulation. On the other side, we have two mechanisms. We've talked about that. Upwelling due to the wind divergence, which are counteracted by the eddies effect. And this is the ventilation. This is what helps the ocean of the interior to be stratified because of this competition and to produce this gradient of density from the south to the north. And in the ocean interior, we have mixing and advection and diffusion effects together with probably intense mixing at the bottom of the ocean, which, unlike what is represented here, is not flat at all. In fact, we have lots of mountains and rocks and troughs at the bottom of the ocean that also favor these topographic effects. So this is one way to model the oceanic circulation based on assumptions about what drives the circulation and trying to write simplified equation for all of these processes. Now that the computers, this was I would say, the early stages, although it is still developed and it's still very informative and interesting because you can have an explicit description of what you want to describe to see how the model, the system responds. But you have another way to do that now that the computers are progressing and our computing capacity is progressing, is to explicitly try to resolve all the equations that are supposed to govern the state of the ocean. These equations are mostly equations of the fluid dynamics with some specific assumptions due to the fact that we are looking at a very specific fluid which is around the Earth. So we are looking at relatively large scales. We are looking at relatively shallow depths as compared to the horizontal scale, etc. So we can make some assumptions. And equations of the conservation of temperature and salinity within the ocean. So this is the second way of doing that, and the models that include all of these equations are called typically models of the oceanic general circulation, that I have a little schematic here. This approach seems nice because at least you resolve everything and you look at what comes out so you can learn about the oceanic circulation and see how it works. The problem is that it implies some approximations. First of all, it implies a discretization of the equations, right? When you compute, when you try to resolve an equation on your computer, what you do is that you cut the system into little pixels, and in fact, you resolve the equations in each pixel, and you just have some exchanges among the pixels and also among the time steps. So there is also a discretization of the time step, and this implies a lot of things, in particular, what size of this pixel do we consider, and what happens at space scales smaller than this grid cell, than this pixel. And what happens at space scales smaller than these pixels or grid cells is represented by so-called parametrizations. So this is an example that is not really appropriate to our problem here, because this shows a pixel for the atmosphere. I am sorry, but I thought it was nice and explicit. This can be considered as a pixel for an atmospheric model, and you can see that in this box, there are clouds that are smaller than the pixel represented by the model itself. So what people are doing is they are trying to integrate the large-scale effect of these clouds on the scale of the pixel and try to find a way to represent the large-scale effect of these small-scale processes. But of course, this is very uncertain. This is ad hoc parameters that are difficult to verify against observations that are most of the time relatively empirical. So we have these two, many other problems, but in particular these two problems that can induce uncertainties and biases possibly in our climate model. And then the question is that the ocean alone, if I do that, nothing happens. I need to put some energy in my climate model, in my oceanic model, so that the ocean begins to move. One way to do that is to impose some atmospheric observations or reconstructions at the top of the oceanic model, and impose some energy, water, and possibly carbon fluxes that come from the atmosphere and help the ocean to be put into process. This is what we call some forced oceanic model. It is forced by observations, and it cannot give any information to the atmosphere. We take the information from the atmosphere. Historically, this is very interesting because, of course, we have a little bit more observations in the atmosphere than in the ocean. The atmosphere is the medium that is easier to observe than the ocean, so historically, observations of the atmosphere are longer than observations of the ocean. Then we have tried to improve these, and we said, okay, but we do have observations in the ocean. We don't have too many, but we have a few. So what about improving these models by adding some observations in the ocean interior? This is called oceanic reanalysis, and I will present in a few minutes results about these so-called oceanic reanalysis. And finally, the problem of all this setup, again, is that the ocean is receiving information from the atmosphere, but in fact, in the real world, the atmosphere is also responding to the ocean. If you have a very warm ocean, for example, this will induce evaporation. Will put humidity in the atmosphere. This humidity can be transformed into clouds, convection, rainfall, etc. So the interaction between ocean and atmosphere is also very important for climate, but possibly for the oceanic circulation itself. So what we have developed also slowly are what we call coupled ocean-atmosphere model or climate models. These are typically the models that are used to do these scenarios of global warming that we have already been talking a little bit about today. And so here what we have our oceanic general circulation model that is so-called coupled to an atmospheric general circulation model that works more or less the same with equations, assumptions, discretizations, parametrizations, etc. All right, so I will try to go through these three types of models to see how do they represent the circulation, what are their biases, and what can we learn from them. So these forced oceanic models, here I show the representation of the stream function that I have showed before. So I remember this is depth here in kilometers. This is latitudes here from 30 degrees south to the north in the Atlantic. And red colors mean that the circulation circulates in this direction, all right? So this comes from, I don't know how many, 3 times 5, different oceanic models that are forced by the same, more or less, atmospheric observations, because these are observations, but these models are developed by different groups in the world, in the US, in Japan, in Germany, in Europe, etc. And this is how they represent the mean circulation. And what you can see, of course, is that they don't agree at all. Well, not at all. They do agree that there is a circulation towards the north in the upper layer, a sinking perhaps, or a downward movement, or at least something happening in the north here, and the return flow around between 1,000 and 3,000 meters somehow, and the cell probably in the other way around at depth. So this is good, it is well represented, but now both the intensity and the exact shape of the circulation is still highly uncertain. And these authors have tried to investigate the reason for this uncertainty, and they have spotted this region here, this region in the northern North Atlantic that we call the Labrador Sea, that has been also highlighted by the previous talks as a crucial region to represent the circulation. So what they show here is biases, so difference to observation, biases in the density of the water in this region as a function of the strength of this circulation as simulated by the models. So none of the models are perfect because of all the assumptions that we've been talking about. Each of these little dots here represents one of the models that I showed just before, and these authors suggest that, in fact, all the models have a very wide variety of intensity of the oceanic circulation, probably because they are not able to represent that well the density and what happens in this crucial region. This is one of the regions. And so then people went back to the observations. You remember Pascal told us that there are some observations in these regions, relatively novel, that are called OSNAP. And so this one here is very interesting because it precisely crosses this region. So the question is, okay, how do we compare two observations? And what we can see here is that, so this is from the observations, and what you can see is that, in fact, in observations, most of the water masses are formed here along these blue sections, and probably here there is not much water mass that is formed. So in fact, this probably shows that the deep water masses that are formed in this region are entering this section and then exiting this section, so that at the end you cannot see anything along this average. And in fact, models are pretty good in representing this. So at least in some of the models, indeed, they do suggest that dense water transformation is mainly done in this region here, and what happens there at least does not feed this southward circulation. So this question remains in a way still open. And this picture, in fact, leads for a crucial role of this current here that flows along the boundaries in this region. And indeed, this is now our view. Since as we are progressing, we believe that a lot of the feeding of this oceanic circulation comes from the boundary currents here around the Labrador Sea. And so, of course, we can say, okay, this current is pretty narrow, is only a few tenths of kilometers. So probably what we need is to decrease the size of the pixel of the oceanic model so as to better represent this current. And here I show you some relatively recent results where now we increase the resolution, so the size, typical size of the oceanic cell from 100 to 10 kilometers. Here you have a series of couple of binom of models. In dash is the low resolution, and in full, the full lines are the high resolution equivalent. And indeed, you can see that the EMOC tends to be stronger in all of the high resolution versions of this model as compared to the low resolution. So there seems to be an effect of this high resolution. The problem is that computer efficiency is still a little bit limited, and we cannot indefinitely increase the resolution. So in a way, for some applications, we have to live with these resolutions. But at least we understand that increasing resolution might help. Nevertheless, you can see that you still have strong differences between the full lines, which are high resolution, and the observations, which are in black here, in particular at depth, for example, but not only. You can see also at relatively high layers. So this is why we thought, okay, it seems to be pretty difficult to constrain the oceanic circulation just by the atmosphere. So let's try to inject some observations in the interior of the ocean so as to constrain a little bit more the interior of the ocean and to better represent this oceanic circulation. And so this is what we call this reanalysis I have introduced earlier. And we use observations that come from various sources that have been partly, nicely introduced just before. The problem that we have is that, if we want to reconstruct the oceanic circulation, we need a relatively long reconstruction. At least we want a relatively long reconstruction for impacts on the climate. And what we have over the last 60 years is only temperature and salinity. So what we can inject are only temperature and salinity. In general, all of these oceanic reanalyses do not inject directly some velocities because these data are too sparse. So what happens when we inject temperature and salinity profiles, this is again the same comparison of a profile of this overturning circulation as a function of the transport here in Sverdrup, and again compared to this rapid array at 26 degrees north, which has really over the last 15 years become our reference for oceanic circulation. And these are various attempts, again by different groups around the world, to try to constrain a non-oceanic model, both by atmospheric observations and oceanic data in the ocean interior. My take on this is that the picture is not much nicer than before. You can see that it doesn't improve a lot. And perhaps what is more problematic, at least for me, because I will eventually be interested in the time evolution of this circulation, as you will see, is what I show here. This is a standard deviation of the hammock. So standard deviation means, this is a little bit of statistics, when you have a time evolution, this is a quantification of the typical variations of a time evolution of a time series, okay? But in fact, this is still a model, so with a model I have a time series at every grid cell of this space. So at every grid cell, I can quantify the variability, the variations, the typical variations of the circulation. And what you can see here, so this is much weaker than the mean transport. We have typical variations of 2 to 3 Sverdrups. But what you can see here is that the typical variations are sometimes very noisy. You see here intense variations exactly at the equator for some reason. Here you have huge variability again in the deep tropics. In this one, it's a huge variability rather at subpolar latitudes or mid-latitudes. Here, there is a very little variability. So with this, I cannot really study the variability and the variations of the hammock because the results are too much everywhere. So the question is, we can try to answer why. We don't really understand. We were really, as a community, a little bit disappointed by this oceanic reanalysis. It's difficult to understand why. I have tried, as I was preparing this talk, I have tried to come up with a hypothesis, or an idea at least, is that, again, we only introduce some temperature and salinity profiles. So, in fact, what we solve, eventually, the transport across a certain section is, as shown before, the integral across as a function of depth of density profiles at all latitudes, at all x. But remember that eventually I then also integrate over x. So at the end, I am really left only by the difference between the density over the eastern boundary of the Atlantic Ocean minus the density profile along the western boundary profile. So these are just two very small areas at the boundaries of the ocean that are poorly observed. In fact, as Pascal was showing, our observations do not manage to go very close to the coast, so that probably the transport is sensitive to observations that are along the boundaries, which are themselves sparse and possibly noisy, and there is no averaging effect, or at least very little. So now let's turn to my third, or the last tool, the most complex tool that I have in my hands. And these are the coupled climate models. So remember, I have this oceanic general circulation here, coupled, so exchanging flux of heat and momentum in particular, because I am a physical oceanographer, so I'm mostly interested in these. There is also exchange of carbon, possibly, with an atmospheric general circulation model. These tools are interesting because they are rather unique to analyze the variations of the system. As I have explained before, they are tools that allow exchanges of momentum and heat and fresh water along the two medium. So they account for air-sea interactions, which are presumably very important for the ocean in general and the oceanic circulation in particular. And they are also very interesting for future events, because all of the models that I have shown before, the forced one and the ones with reanalysis, are based on reconstructions that we have. So they cannot go into the future, because in the future we don't have more observations of the atmosphere than in the ocean. Okay? So this is why these tools are really the ones that are used for going into the coming century, as shown in this graph already. All right, so let's go back to our favorite profile, comparing to rapid. And this is again and again, now you are used to it, the transport in Sverdrup as a function of depth at this specific latitude, 26 degrees north, where we have this rapid array. And now this time it is in thick purple here, you have the rapid array. Okay, not much surprise here. You can see that all the various climate models that are available around the world are also very much, show very strong differences in terms of representing this profile. In a way, one could say that this result is not so bad, because remember that as opposed to the two families of models that are presented before, here there is absolutely no observations. There is really only the equations of the oceanic dynamic and thermodynamic, atmospheric dynamic and thermodynamic interacting together as well as we can do. All right, so still the same question. You could say, okay, but all these are relatively coarse resolution, because we want these models to be not too expensive so as to be able to integrate them over relatively long time scales into the future, and also to really understand the long variability of the ocean. But we are doing some tests with higher resolution. So the question is, does resolution help? And here I show you just a comparison of two different resolutions that have been performed at IPSL, the lab that is standing at Sorbonne University just across the street from here. We are developing our own model there and trying to contribute to all of these inter-comparisons. And here you can see in red, this is our low resolution version. And in blue and green, these are two flavors of our higher resolution version. So here we have increased the oceanic resolution by a factor of 4. And you can see that, in fact, these high resolutions are still uncertain, because here there is a question about which parameterization do we take. We have been trying two different parameterizations for this subgrid scale. And you can see that, in fact, apparently the effect of changing or not this parameterization is stronger than the effect of the resolution, because in the end, our best estimate is not much better as compared to observations than the low resolution. So resolution doesn't seem to do it all, and there is a full area of research here in terms of improvements of subgrid scale parameterization, representation of the coupling, tuning the model, calibrating the parameterizations, etc. All right, so in the few minutes that I have left, I will finally come to the variations of the oceanic circulation. We've been saying that the oceanic circulation has probably varied in the past, will probably vary in the future. Here I show you a sort of a schematic, so it's a pretty busy plot, I agree, but I will try to guide through it slowly, and we will look at what we need to look at here. So on the vertical axis here is again the standard deviation, so this typical amplitude of the variations of the circulation of this large-scale oceanic circulation. This scale is a bit weird. This goes from 1 to 7 here, and then from 10 to 50 here. It's a nonlinear scale, but that tries to quantify the typical variations that we believe are happening, from models and the few observations that we have, in terms of this oceanic circulation. And this standard deviation here is given as a function of time scale, because the oceanic circulation is there every day, every second, every minute, every century, and is varying at all these time scales. And in fact, what you can see is that, and this red interval here is a sort of a measure of uncertainty from the various sources that we have been using for computing this plot, and this is coming from an average of models. And what you can see is that at very fast timescales, at a daily timescale, the ocean is varying a lot, right? It is, I mean, this oceanic circulation, large-scale oceanic circulation, typically varies from one day to the other by 15 Sverdrup. So 15, 10 to the 6 cubic meters per second. And then as we go to slower timescales, so to yearly timescales, decades, centuries, and millennia, the typical variability of the oceanic circulation decreases. So one could say, okay, but then why are you interested by long timescale? Because it seems that the short timescales, in fact, are more energetic and more important. This is because in parallel to this graph, these people have been trying, again, with a huge range of uncertainty because it is a little bit of an empirical study, but I like the idea it carries. They have been trying here to quantify the relevance of the AMOC variability now for climate, the influence of these variations for climate. In fact, what happens is that this strong variability that occurs at very fast timescales is probably not so important, at least directly, for climate. What is important for climate seems to be rather what happens at yearly and longer timescales, decadal timescales or longer. This doesn't mean that we don't care about these, because probably what happens at very short timescale has an effect also on the long term because of averaging effect on the decadal timescales. But still, what this graph shows is that although variability is not so strong at these timescales, the relevance for climate increases. And this is why, at least myself as a researcher, and what I will show today focuses on these timescales, decadal from centennial timescales. Okay, so what, at least for today, we can focus on that. What do the models say? Here, I show you not directly the AMOC, time series of the AMOC modulation, but rather a time series of this temperature average here in the North Atlantic, which is exactly what Pascal has called AMV, Atlantic Multidecadal Variability, this typical variation of the temperature of the surface of the sea that is associated to large-scale circulation. We know that when the circulation varies, when this large-scale circulation varies, AMOC, there is a strong impact on the temperature averaged over the North Atlantic. And here I show a time evolution of these temperatures in two simulations of the climate, which are both performed, again, across the street at Sorbonne Université in the IPSL modeling group. But this is the model that we have been developing about 10 years ago, in the 2010s. And this is the latest version of our model that we believe is improved, but who knows, that we have been developing in the years 2020s. And now these curves here are completely flat because in these simulations, there is no increase of greenhouse gases. That's the good thing with model, is that I can really be a pure physician and I can stay in my climate system completely stable and only look for interactions and drivers in terms of the physics and not at all in terms of external influences to the climate system. And what I find interesting here is that you can see that in the 2010s, we had this long time scale that typically varied on a 20-year time scale. You can make a spectra of this time series, and there is quite a nice peak at 20 years. And here on top, the years correspond. Okay, I think I have tried, if this is well done, I have tried that this time scale is similar to this one, and you can see here that the variability is much slower. So now our model represents a typical variability at centennial timescales. We are not completely sure why. We can understand this variability and see, okay, what is varying and what is happening, but it is not completely clear to us why there is such a difference between the two flavors of the IPSL model, and this is still an area of research, and we still have uncertainty in terms of the typical frequency that is modeled for the oceanic circulation. All right. So some people have been trying to look at that, and this is a paper by a colleague where he has tried to go through 18 studies that are published in the literature, 18 different groups that have been investigating in their own climate model what is the time scale of variability of the oceanic circulation in the North Atlantic, and what are the typical mechanisms. So this is a summary, whether it comes mostly from the ocean or whether it implies the atmosphere. And here you have some keywords of the typical mechanisms that are involved in this variability. This paper is already a little bit outdated, but still you can see a very wide variety of different mechanisms. Some of them are purely oceanic, like this one, and typically what happens here, these people have shown that it is probably due to anomalies here of temperature. For example, if you have a warm anomaly here somewhere in the east of the Atlantic and a cold anomaly somewhere in the west of the Atlantic, this induces a northward anomalous velocity. But because on top of that you have a mean velocity that carries this whole system towards the east, then in fact the temperature anomalies are going to shift, and you can see that this V is going to be in the middle of the warm anomaly, so it's going to decrease to 0, and then possibly the opposite system will come, and so you will have an anomalous circulation towards the south, and you can have like this a sort of an oscillation of the large-scale meridional velocity because of east and west anomalies of density on top of a mean current. This is a typical mechanism that can explain partly, that we have found that can explain sometimes the variations of the EMOC in the models. What I find interesting also in this schematic is that now we are back with our Labrador Sea that we've been seeing quite a lot now. So I've been saying, okay, possibly most of the water mass is transformed, in fact, further upstream, at least to explain the mean circulation. But to explain the variations, at least climate models seem to say that the Labrador Sea is still very important to explain the modulations now of this circulation around the mean. Okay? So, why is there such a crucial role of the Labrador Sea? Typically, it is a response of a specific atmospheric pattern that is the North Atlantic circulation. And I take this example to carry you through another type of process, which is the influence of the atmosphere on the ocean. The atmosphere is as the ocean, it is a fluid, it varies, and it varies typically through large-scale modes. And what we find relatively often in the atmosphere is, so this is a map of typical sea level pressure, so the pressure of now the air mass and not the water mass in the North Atlantic area. You recognize Greenland, Europe, and America here. And typically what we have about 30% of the time is a little bit less than average pressure or lighter air masses on top of Iceland and the subpolar North Atlantic, and heavier masses on top of here the subtropical Atlantic. This is called the North Atlantic Oscillation. It is the dominant mode in winter over the North Atlantic. So this is what happens most often. And it is a sort of a seesaw like this of atmospheric masses between the subpolar and the subtropical regions. And associated, in fact, to this anomalous pressure, exactly as when we are looking at meteorological maps, there are anomalous intense winds that come in this region, and these anomalous winds are associated to a very strong flux of heat out of the ocean because of enhanced winds that, on top of everything, come from the Arctic, so they are relatively cold winds. So this creates, so this map is again pretty busy, I apologize. Again, these anomalous winds create typically cold temperatures in this region, and cold temperature in this region means relatively dense water masses. Okay, denser water masses are colder, so they will more easily sink at depths and fuel the oceanic circulation. So this is typically the story of how the atmosphere modulation can feed the oceanic circulation. Perhaps some of you here are physical atmospheric scientists, And they say, but how is it possible that the atmosphere that varies at very short timescales, we've been talking of days before, how can this very quick changes in the atmosphere, because of course the NAO that I have been showing just before, this one doesn't persist like this for decades. So how can it influence the oceanic circulation on very long timescales? How do you go from something that varies very quickly to something relatively slow? In fact, I have avoided any equations here, but I should just show you the result. If you write the equations of the oceanic circulation, you can see that when you impose a typical atmospheric forcing time series like this that we call in statistics a white noise, or something that varies randomly from one day to the other, in fact, the oceanic integrates this large-scale, this very fast varying atmosphere, and the typical time variation of the ocean is much slower, around decades, as opposed to the ocean. The ocean to the atmosphere. The ocean plays the role of an integrator of the atmospheric noise. There are many other possible processes, and I will not be too long now. Again, this was just a short story of what can drive modulations of the oceanic circulation. This is an example of a study we have been carrying earlier, some years ago, where we have shown that there is also, so of course it is busy and you're not supposed to understand it in details, but the idea is to show that sea level pressure, so the atmosphere, can also drive anomalies of the oceanic currents. This is the East Greenland current that flows in this region. This anomalous current brings cold water in this region. And then you also have an interaction with density in the North Atlantic. In this model, we also had interactions with density at the western and eastern boundaries, as I have said before. So this schematic is here to tell you that all of the different mechanisms can also play together, interact, resonate, or cancel out, and this leads to the complexity of the oceanic circulation. Last not least, the Atlantic is connected to the rest of the world, and this is a variant study that we have been carrying as well in my group, where we have been imposing some anomalous temperatures in the Indian Ocean. So we said, okay, what happened if the Indian Ocean was warming artificially by, warming by 1 degree or cooling by -1 degree. So we impose artificially in the model. This is what is nice also with models, is that you can do these experiments, sensitivity experiments. So we imposed a cooling here and the warming, and we could see, so this is the cooling experiment that is shown here. This is the warming experiments. We have 2 sensitivities for the warming and 2 sensitivity for the cooling. We can see that the intensity of the oceanic circulation in the Atlantic could be increased or decreased because of this influence of the tropical Indian Ocean. The mechanism is, again, a long story, either directly through atmospheric waves directly to the North Atlantic, or possibly through tropical atmospheric waves in the tropical Atlantic, and then a story of oceanic advection through the Atlantic. And this is, again, a full area of research. So I would like now to give you a few conclusions and research perspectives. First, we have seen, perhaps a take-home message is that the EMOC variations at the decadal and longer timescales have substantial climate impact, and that oceanic and climate models are still valuable and unique tools to understand the drivers of these circulations, in spite of biases. Probably, I still believe that EMOC mean state and variations are largely associated to dense water formation in the northern North Atlantic, although the exact role of the key locations is not completely clear. The Labrador Sea, does it play on the mean state or only on the variability? I could do the same story in the Nordic Seas, so all these are still relatively open questions. EMOC and the oceanic circulation in general is a complex beast. That implies interplays and many processes and mechanisms, so it is still relatively difficult to understand. And it is the problem that we have also with the numerical models is that it is still difficult to assess the robustness of the EMOC in the numerical models. Yeah, and the problem of resolution and structural choices. Climate models are still very important to anticipate our close or more extended future. This is an example of an experiment where we have tried to see if the internal variability of the circulation is predictable. So here, the black line is no observations, but is a kind of a reference simulation. And what we did here is we have tried to perturb the initial state of the oceanic circulation and run the model another time to check if the model was able to reproduce the same trajectory for the oceanic circulation. And you can see that, on average, yes, more or less, you can reproduce at least an intensifying anomaly, but not the amplitude of this anomaly. So what part is predictable, what part is not predictable? Here, this is at decadal timescales. Okay, here I was 15 years before the peak. But of course, ultimately, what I would like to predict is these type of variations at centennial timescales at the end of the century. But then, this is another story that I will not, investigate today with the effect of external forcing and in particular the CO2. Thank you very much.